Welcome back to today's Explainer. Today, we're basically putting on our scientific detective hats to investigate a bold new diagnostic tool for artificial intelligence. It's called the SICT framework. If you've ever found yourself wondering exactly how researchers are trying to peer inside the chaotic, totally mind-bending architecture of large language models, well, you are in exactly the right place. Let's get into it.
All right, before we really get going, I want you to think about this for a second. When an AI makes a decision, it uses these internal feature spaces that are notoriously unstable and incredibly hard to map. Imagine trying to draw a map of a city, but the streets literally rearrange themselves every single time you blink, right? So how do we know what's actually going on inside? How do we measure the health of an AI's representation when the underlying geometry just keeps shifting? That is the exact puzzle this framework is trying to solve.
Okay, here's our roadmap for today. We're going to hit 1. Diagnosing the AI black box. 2. Meet the SICT framework. 3. 5 levels of observation. 4. Tagging the truth. 5. Defending the science. And finally, 6. The ultimate falsification test.
All right, Section 1, Diagnosing the AI black box. Let's look at the exact roadblock this research is aiming to solve.
So right now, to peek inside these models, researchers usually use tools called sparse autoencoders, or SAEs, to break down the AI's activations into readable features. But well, here's the massive roadblock. These tools give fundamentally different results depending on the training seed. That's the AI's initial random starting point. Or they'll change based on the specific checkpoint in its learning process. They are inherently unstable, and you can't exactly build a rigorous science of AI on quicksand, right? So we desperately need a protocol that directly addresses and accounts for this instability.
Now, check out how perfectly this visualizes the SICT solution. The authors, who are out of the Roth Complexity Lab, basically propose building an MRI for AI. It takes those chaotic internal states and organizes them into 5 distinct levels of analysis, alongside 4 measurable metrics. To be clear, this isn't some new way to train an AI. It's a standardized vocabulary. It's a diagnostic lens to summarize the geometric, informational, and dynamical state of a model.
Moving right along to Section 2, Meet the SICT framework. Let's actually deconstruct this acronym to understand the specific metrics they're using to examine the AI.
First up, the S stands for structure. This metric gives us a really solid mathematical grip on the geometry of the AI's feature space. We're not just staring at random numbers here. We're measuring the fundamental shape of the data. It's kind of like looking at the foundational blueprints of a building to see how clustered and modular the features are. Basically, it answers the question, what is the shape of the data?
Next is I for information, because once we figure out the structure, we kind of need to know what it's actually doing, right? This metric measures the entropy and mutual information. In everyday terms, it answers exactly how much usable, relevant data is actually being carried by these internal representations to perform a given task.
Then we have C for cohesion, and this one is absolutely vital. Remember that quicksand problem we just talked about? Cohesion directly tackles that seed instability issue by tracking internal consistency. It measures whether features actually hold together across different layers of the neural network and, critically, across independent training seeds. Simply put, if a feature vanishes the second you change the random seed, it's got low cohesion. Finally, T is transformation. This is all about capturing the dynamic movement of the AI's representations. It tracks trajectory, curvature across layers, monitors how much the features drift across different training checkpoints, and, this is super cool, it measures the sensitivity of the system when subjected to causal interventions or ablations. Meaning, what happens if we intentionally yank out parts of the network? How does the system react? It's the ultimate metric for measuring change.
All right, Section 3, 5 levels of observation. Let's see how these metrics stack up as we climb from basic reality all the way up to pure abstraction.
Look at this ascent of analysis here. We start way down at the ground floor at level 0, the behavioral layer. That's just the plain inputs and outputs we can all observe. Moving up, level 1 maps the activation trajectory. Level 2 explores intervention space or counterfactuals. Level 3 is the latent feature space. Now this is precisely where our SIC and T metrics actually get measured. And the whole thing culminates at level 4 in a curated version diagnostic catalog. One quick caveat. Inspired by the philosopher David Marr, these are strictly analytical levels. They are absolutely not physical dimensions.
Section 4, Tagging the Truth. This is where the framework performs a brutally honest self-audit of its own scientific claims.
Okay, this is actually incredibly rare and honestly so refreshing in academia. The authors literally clean house. They explicitly toss out their past speculative physics claims, things like assigning integer dimensions to a 7D multiverse, or claiming they found some universal Platonic stability law. They realized that stacking metaphysical concepts into numerical dimensions was just a massive category error. So by tossing all that out, they leave behind a highly grounded, totally defensible methodology that focuses purely on empirical AI representation analysis.
So the crucial takeaway here is this epistemic rubric. They rigorously tag every single claim in their framework as either established, grounded, heuristic, or speculative. Notice how the basic inputs and outputs are rock solid. They're established. The SEIC feature decomposition at level 3 is grounded. The actual naming of the SICT axes, they admit that's just a heuristic. And that old rule they used to tout, where S plus C is greater than or equal to I plus T, they frankly label that as speculative because it didn't have a first principles derivation, so they demoted it to a simple tunable baseline. This ensures absolute transparency about what is mathematical fact and what is just a working theory.
Which brings us to Section 5, Defending the Science. We're pivoting from AI mechanics over to philosophy for a second to ask, is this actually real science?
I love this quote from the philosopher István Toth. He basically highlights that the clearest sign a framework is legitimate science is its willingness to publish adversarial audits that refute its own earlier claims. Think about it. Pseudoscience constantly hides its flaws and avoids tests, but a huge chunk of the SICT published corpus is exactly that, self-administered refutations, where they literally test their own framework to destruction and then publicly publish the failures.
So how does this build a philosophical foundation? Well, instead of a strict Popperian test, where one single failed prediction instantly kills an entire theory, this operates as what philosophers call a Lakatosian research program. It builds credibility over time, it uses explicit falsifiers, continuous self-correction, and what's called abductive reasoning. That just means it proposes an inference to the best possible explanation, rather than strutting around claiming definitive magical proof right out of the gate.
And finally, Section 6, the ultimate falsification test. This is where the rubber meets the road, outlining the exact criteria that will determine this framework's future.
To upgrade this from an abductive proposal, a really educated hypothesis, to confirmed inductive science, the authors explicitly say the framework has to hit 3 rigorous steps. First, they have to operationalize one variable fully into a reproducible 0-to-1 scale. Second, they have to derive a totally novel prediction that no generic competitor could possibly make. And third, they have to run a decisive ablation test, systematically removing variables to see if the whole thing just falls apart. And if it fails these steps, the authors state up front, it must be completely rejected. No excuses.
So I want to leave you with a final thought for today's explainer. This diagnostic lens has literally set the stage for its own survival or its own destruction. By explicitly laying out the exact conditions under which it should be thrown in the trash, SITT makes itself true science. So the lingering question is, will this framework actually uncover the true hidden mechanics of AI, or will its own rigorous self-imposed tests prove it entirely redundant? We'll just have to wait for the data to find out.